All right, let's take a look at another value iteration example, this time with our fine grid world. We're using the same basic equation, and as before, we're going to be starting off on the leaves down here, and so we're going to initialize everything with every value as 0. And as before, what we do is we apply this equation to each state and move ourselves back up the tree. And so we'll look at the chance nodes, develop the Q values, which I will write there, and then the max will take the action that maximizes its reward, and so that value will then replace this Q value. Now remember that we were evaluating an entire level first on the tree, so that when I get a new value for, say, this square, I don't use that value in calculating these others. I still use the old value of here till I've got new values for every square, and then I replace them all at once. So where should we begin? Well, we could begin over here at the start, but we notice in the equation, of course, there's no reward anywhere near this action in the start, and the neighbors have no value in them either. So this is going to end up being all 0, and we're just going to end up with a 0. And that's the same for these states as well, because they're all none of these states are next to a state with value or next to something that provides a reward. But what states do have possibility of taking new values in the next iteration are those 3. So let's start with this data up here and just start generating the Q values. So we need a pen. We can find the Q value of state 3, and action east, and so what do we have there? Well, it's a sum across of the transition table. So that's, let's see, 80% of the time it does go east, and it gets a reward of 1, and that's plus a value of 0 because that's a terminating state, so there's no future reward. Plus 10% of the time it goes north, bounces off the wall, and ends up in the same square, so that it gets no reward plus no value. Plus 10% of the time it goes south down here, but there's no reward there and there is no value there. So this means that the Q value for going east is 0.8. All right, so what about the Q in 3 for going north? Well, 80% of the times that works. Bounce off the wall and end up back in this state, which is a 0 reward and 0 value state. And 80%, or 10% of the time, it goes west, and that ends up being a 0, 0. And 10% of the time, it ends up going east, which is 1 times the reward plus 0. So actually there is some value, Q value, for going north, and that is 0.1. Now what about going south? Well, 80% of the time that works, no reward, no value. 10% of the time we end up going west, and that's no reward and no value. And 10% of the time we end up going east, which is a reward and no value. So we get a value here also for 0.1. And then finally, the Q value for state n going west. Well, 80% of the time that works, and that's 0, 0. 10% of the time it goes north, bounces off the wall, and ends up back in the same state, and that's 0, 0. And then 10% of the time it goes south, no reward, and no. So that ends up being a whole lot of 0. So what we get is the maximum of those 4 values, which for this square ends up being 0.8. I'm writing that next to the 0 and in green because, remember, we're still going to be using this 0 to be calculating the neighbors. All right. So now we've done this for one square. We know that most of the other squares are not going to change this iteration. So what we should do then is take a look at these two squares. So first, starting with this, 2, 3. Right. If we go east, we get 0.8 times -1, -0.8, plus 0.1 getting 0 and 0.1 getting 0. So we get -0.8. And Q in 2, 3 going north is 0.8 at the time you get 0, 0.1 at the time you bounce back and get 0, 0.1 at the time you go here, and so that is worth -0.1. And Q of 2, 3 going south is also equal to -0.1 for the same reason. But finally, okay, Q of 2, 3 going west is actually, well, 80% of the time you bounce off the wall, go here and get 0, 10% you go up there and get 0, 10% you go down there and get 0. So in fact, actually, its value is 0. And so what's the Q value of this? Well, the Q value is the max of those 4 things, which is, in fact, because 3 of them are negative, the max of them is 0. So in fact, it didn't change at all. And we'll see that this happens in the same way here, just as this is the safe, going west here is a safe move to make, going south here is a safe move to make, and so you can always do that, and so the max, so in fact these do not change. The only one that changes is this one up here. All right, and so everything else is 0, so when we're done with our first iteration, we have situation like this. All right, now we've actually computed the next layer up. We've got the values of the max nodes all up 1 from the leaf. Now what we need to do is move up again. So we repeat the process of the value iteration and take it from there. So same as before, a lot of these states are not next to anything with any value or any reward. Oh, this one is next to something with a value now, and this one is next to something with a value now. So they're going to have new things. This one we know is going to be stuck at 0 again because it will take that southerly move. But so we run the iterations again to see what we get, and so we can always start here at this one because that was where we started the last time. And what do we say? We say, well, what's the Q value of 3, 3 going east? And that's 0.8 times 1 plus 0, right? Same as before. And if 10% of the time we end up going south and end up in 2, 3, and that is 0.1 times 0 plus 0. All right, so this is exactly the same as before, but now 10% of the time we're trying to go east, we accidentally go north, and we land back in this square. And look, there's a value actually in this square now, so it's 10% of the time, no reward, but a value. Oh wait, so now we actually have to incorporate because it's actually gamma times the value. Did we say what gamma is? I don't think we did. So let's make gamma be equal to 0.9. All right, so 0.9 times 0.8 is 0.72, which gets multiplied again by 0.1, that's 0.072, so this actually equals 0.872. So this updates a little bit, 0.872. Notice I only checked one of the Q values here just to save time. We know that this Q value is going to be lower and that Q value is going to be lower, and so this 0.872 is going to be the max. All right, now next up, we need to compute the Q of 3, 2, right, going east, and again, that's 0.8 times, well, it's 0.8 times, there's no reward here going east, but there is a value there of 0.8 times the gamma of 0.9. This is then added to 0.1 times going 0, bouncing off the wall, and 0.1 times 0, bouncing off the other wall. So this gives us a new Q value of 0.576. Now in state 2, 3, we actually have an interesting question, which is it better to go north, get that value above you, but with the risk of falling into the pit, or to stick with our going west strategy, knowing that 10% of the time we'll still get a little bit of that up there? So take a guess, and let's see how it works out. So let's take a look at north is 0.8 times 0 plus 0.9 times 0.8, just as with 3, 2. And we've got we could go to the west, 0.1 at a time, gives it back to 0, and now we've got something interesting. We've got 0.1 at a time, we go east, and of course that gives us a reward of -1, for a total of 0.476. Now what about 2, 3 going west? Well, that's 0.8 times no reward, gamma's 0.9, but we bounce off the wall and end up right back in 2, 3, which is currently 0, so that's still 0 again, and plus 10% of the time we go south, and that's worth 0. And 10% of the time we go north, which is 0.1 times 0.9 times 0.8, which is 0.072. So we can see that clearly we actually do want to take the move up there to make that action and risk falling into the pit. And now, since all of the other squares still don't have any values next to them that are going to affect them, remember this guy's going to go straight down there, that we're done with this iteration and we can update our value. And we repeat this process, which I will have you do in the problem set to continue from here. Some things to note, notice how this square is still, it's going to go up a little bit every time, right? That because now before when it bounced off the wall it got 0.8, but now when it bounces off the wall it's going to get 0.872, so that's gone up a little bit. But notice that's also discounted by a 0.1, and so that this is going to go up a little bit each time, but each time it will go up a little bit less until finally the moves upward are imperceptible, and we say that this value is converged. And notice these states that the value is kind of sort of spreading across, and it will spread eventually all the way over to the start, and then even the start will eventually converge on the values. Now start's value will be much lower here than here, even though it has a perfectly safe path, because of course the gamma has been reducing it on each step of the way. And so that's how we run value iteration on our grid world. And our secret passphrase is moronic overestimate. That's 2 words, moronic overestimate.